Kirk Math. Hey guys, we are starting 6.2 now. We're going to start graphing our exponential functions, so functions that have exponents. You are on page, I believe, 120 and 121 of your student companion, and we're doing the whole lesson today, so one video. So here in the first example, we're just going to take a look at a function with an exponent. So what does f of x that equals 2 to the x power look like? So the first thing we're going to do here is make a table and start graphing points. So in this table, you can see right here, they started with -2. And you have to remember that when I have an exponent that is negative, so my problem would be 2 to the -2nd power, that makes it a fraction. Okay, because I'd actually get 2 to the power of 2, 1 over 2 to the power of 2, and that makes 1 to the 4th power, 1/4. Okay, when I have a -1, I'm going to get 1/2. If my exponent is 0, 2 to the power of 0, again, because of our properties of exponents, I know that that's going to equal 1. So that is where our y-intercept comes in, okay, because when x is 0, then y will be 1. And then, as you can see, as I get into these higher and higher numbers, my y value is growing so quickly. It's going so fast. And you guys know that because even just 3 to the 3rd power is way larger of a number than you would think it would be. Because you would have 9 times 3, which is 27, and we start making these really big jumps as you go up. 3 to the 4th power is going to be 27 times 3, right? So 7 times 3 is 21, 2 times 3 is 6, 7. So now I've got 71. So you can see that these jumps as I go up become faster and faster, which means that my graph is going to become steeper more quickly. Okay, if you've ever heard the phrase that it's growing exponentially, it means that its growth is faster and faster every time. It's going up by more every time we do it, because as my exponents go up, my y value, my answers grow really quickly. And here's the graph here that you can see. These are the points that they have on the left. And if I start to zoom out, you'll start to see how steep that line goes. We're almost vertical at one point, right? What you'll also notice, though, is that back here, as I am in my negative exponents, I'm always going to get a fractional answer, which means that I'm never going to get to 0. As the x value approaches negative infinity, negative meaning it'll be a fraction, the y value approaches 0, but is never truly equal to 0. And again, as I zoom out, you're going to see, look, this line is it kind of looks like it's on the line. We're never going to get below, because my fraction is just going to become a larger denominator until, as it gets closer to 0, I might have 1 over 5 million something, right? 1/5,000,000th, right? We're going to keep getting these fractions that are really close to 0, but we're never going to get to 0. And that's kind of a common error here that people don't realize, is that when you're graphing these exponential functions, you don't exactly have a y-intercept. You can get pretty darn close to 0. You could even say that right here where our line, if I start zooming in, you can see, we could start to say, well, maybe -6, we can approximate it, but we're never actually at 0. And again, if I zoom in, you guys can start to see this is not touching 0. I'm getting closer and closer, but then as I zoom in, oh, I'm still not that close, right? I'm getting fractionally a smaller and smaller fraction, really close to 0, but it never equals 0. So that is what a graph of an exponential function looks like. It's going to look like this drastic curve, okay, where the line and its slope increases very quickly, okay? If the exponent is 0, then the answer is going to be 1 no matter what. So its y-intercept is going to be 0, 1. And it's never ever really going to have an x-intercept, okay? All right, that being said, there are some characteristics of this exponential function that we can kind of look at. So it says the graph of f of x is equal to 2 to the x power is continuous between and beyond the x values shown. So the domain is all real numbers, meaning I can go as far left or as far right as I need to. There's no numbers that are excluded, okay? So all real numbers is my domain. Then when the function gets closer and closer to the x-axis, it never quite reaches it. So the function approaches a line in this manner. When this happens, the line is called an asymptote. Okay, so this is the word you want to write down, and its definition is right here. When a line or a function gets closer and closer to the x-axis, but it never quite reaches it, it's an asymptote. Asymptote. I'd have to look up the definition. I think people say it differently. The asymptote of f is y equals 0 of this function. The range is y has to be greater than 0 because y cannot go down below 0 here. Sometimes you're going to get an exponential function that's on the opposite end that curves down below. Okay, then you would have that y would have to be less than or equal or less than 0. Okay, you're going to see that there. Sometimes you're going to have ones that are going to go the other way where it never touches y. So that's why it's saying this asymptote here is 0 because it's never touching 0, and that its range is greater than 0. All right, because this word can get pretty confusing, I did a really quick Google search here to kind of see if there was a simple way to explain this. But an asymptote is a value that you get closer and closer to but never quite reach. In mathematics, an asymptote is a horizontal, vertical, or slanted line that a graph approaches but never touches. So you can kind of see in this image, right, that this line is the asymptote of this graph. This line is the asymptote of this graph. They get close to it, but they never touch it, okay? That's kind of what that means. So when we talk about what the asymptote is, that's what we're looking at. That's why back on this problem, it tells you that the asymptote is y equals 0 because the having y equals 0 is the thing it's never going to touch, okay? Which means that all the y values have to be greater than 0. Okay, so I want you to try this problem right here. You're basically just looking at two graphs that have an exponent of x, an unknown value that could be anything. We're going to look at the function for the two things, if the base is 2 versus if the base is 1/2, and I want you to verbally explain them, or written explain. Explain their domain, explain their range, tell me what happens when x is a certain value, tell me what happens when y is a certain value. Just give me a description about the difference between the red line and the blue line. So I went ahead and graphed them for you so that you didn't have any mistakes, but if you were graphing this by hand, let me erase over here so I can kind of show you. You would basically just use a table to fill in the information, okay? So you would just make tables like this, okay? I like doing the H tables because then you can see the work in the middle, but it's basically just input and output. If I have -2 as my exponent of x, that would be 1/2 to the -2 power, that would make 4, okay? And anyway, so once you do these tables, you would graph the points here, but you can see this is my red, my orange line right here. This is the graph of what it looks like when you have a base of 2. And then the blue line is what your graph would look like when you have a base of 1/2. So on your student companion, I want you to write out the differences between the two graphs, the domain differences and similarities, the range differences and similarities, and then explain and describe the graphs for me. How are they different? How are they the same? All right, so here's some basic concepts for you. Now, we don't usually have this right away, but I wanted to go over this before we go over other things. So this is a good thing to take down for your notes. An exponential function is the product of an initial amount and a constant ratio, raised to the power. Exponential functions are modeled using this model right here, where a is a non-zero constant, and b has to be greater than 0, but not 1. Okay, so this is your initial amount. If you remember in our slope-intercept form problems, when you have y equals mx plus b, b is also considered your initial amount. Okay, but in this case, for our function, a is going to be your initial amount. And then b, this is going to be basically your slope. And I know that letters are weird. I'm sure Miss Falk would know why these are both B's and things like that. But this is actually our slope because this is our constant ratio, but it's not being multiplied anymore. It's being raised to a power. Okay, so we're going to go ahead and take our information about exponential functions and we're applying it to a word problem here. So we have a network administrator uses the function f of x is equal to 5 to the x power to model the number of computers a virus spreads after x hours. It's exponential because it starts with 1, spreads to 5, those computers spread to 5, those computers spread to 5, and it grows exponentially. 5 times 5 times 5 times 5. If there are 1,000 computers on the network, about how many hours will it take for the virus to spread to the entire network? So in order to solve a problem like this, you're going to start by making a table. Okay, kind of like our H table that I made over here, but we just have our X, and then you've got your formula here with your answer. Okay, you could make it H if you want to just throw in your work here and then add your answers to the right side. That's fine. The next thing you're going to do is graph that function. Okay, and you're going to use that graph to figure out that when y is 1,000, x is approximately 4.3. And then you can double check using a calculator. Okay, 5 to the 4.3 power would make this right here, which is as close to 1,000 as we can get. Okay, so therefore it's going to take about 4.3 hours. Obviously, this is the 4.3 is an approximation. They're just kind of estimating, right? When this is right here on this line, I'm coming down here and saying that that looks like it's about 1 1/3 over to the next number. And that's where they got the 0.3 from. But making a table and making a graph is how they found their answer. So take a look at this one, okay? So what about if I needed to get to 50,000 computers? Can you make a table? Can you graph it? Can you find an approximately when that would work? Now, of course, we have to go back the other way. So we want to take a table and I want to write the function formula for it. Okay, so I'm going to take this table and I'm going to look for the change each time. Okay, if you look, I'm dividing. The initial amount is 4. Remember, my initial amount here is A. That's blue. It's their color coding. And my change, or my slope, is by 3. If I divide 4 by 3, that goes up by 3. If I divide 36 by 12, that goes up by 3. We're multiplying by 3. That's my constant ratio. That's going to be my B, my slope. So it's very similar to slope-intercept formula, except using exponents. Okay. So I'm going to take the 4 and put it here. I'm going to take the 3, and this is going to be my function here. Note that exponential functions have constant ratios rather than differences. So instead of subtracting, we're not looking at addition here. We're looking at ratios, multiplication and division. So this is going to be a graph, and I have to write the exponential function of this graph. Same thing, I'm looking at the initial value where it's starting on y. That's my A. Then I'm looking at the change between each point. Okay, it's changing by half when I divide 64 by 128. That's half because we're decreasing. That's going to be my slope, basically, and then that's going to be my exponential function. So here you're going to take these values. You can put them in a table. You can make a graph, whichever one you think will be easier. And these values here, and you're going to write the equation, the exponential function, for these two sets of data. And in the last part here, because we know that slope-intercept form and this exponential function have some similarities, they're just comparing these two options. So here we have slope-intercept form, just a regular function, and over here we have an exponential function. And by using tables, we can compare the two pieces of information to see that option B is constant. The exponential function will increase faster over time. So for this situation, the exponential one is a better choice. And then you're just going to give it a try as well. Okay, you're going to make tables for both of these and compare them and identify them as either linear or exponential.